Hi, it's Alexander, and in this video, I will show you a brief explanation about RIP protocol. Okay, RIP protocol will be studied, its different features and characteristics, the scenarios where it's applied and the ones where it isn't, as well as the difference between RIP version 1 and RIP version 2. A brief review of its strengths and weaknesses compared with other routing protocols will be done in a quick explanation of implementation through an example. The Routing Information Protocol, as known as RIP, is a distance vector protocol created in 1981 as a response for the need to a simplified routing information protocol. Defined in the RFC 1058, it's well known as an easy way to configure and use in small networks. As we all know, the distance vector may present some issues like the infinite counting loop, where two routers pass information between each other without stopping because of the absence of the third router, which is supposed to be working. That is one of the reasons why RIP has a low convergence. Since RIP's metric is based on number of hops, the infinite counting loop could be considered tolerable. This is not as critical as using a more sophisticated metric where the range of values it can take is wider. By the time of its creation, it was considered that 15 hops was more than enough for the maximum number of hops. Nowadays, this number was surpassed for the needs of the current networks, but it's still okay for small network applications. The distance vector information is exchanged between each router every 30 seconds exactly, but it can lead to a very singular situation occurring. The expected behavior is that each router starts working at a different time from the rest. But it could happen that all the routers start working at the same time, synchronization, causing network congestion or blocking during distance vector exchange time. The creation and implementation of new technologies originated an update for the protocol called RIP version 2, which supported those new features like classless and subnetworks. After that, when OSPF came out, it was expected the end of the RIP routing protocol. However, then RIP NG or next generation was released with support for IPv6. Despite this, RIP doesn't support traffic balancing. Here is an implementation example of the RIP protocol. As we see in the picture, we have just 3 routers, Daule, Guayaquil, and San Borondón. And we also have the routing table. In the first slide, we can see the results obtained after executing the command ping from each one of the routers through the IP directions or IP address and the loopback's address, verifying in that way the connections. After that, we configure RIP version 2 on each router in order to let the updates regarding to subnetting masks. In this slide, we can see the evidence of the RIP version 1 and 2 support on router San Borondón, as well as the implementation of the no autosummary command. In the next slide, we can see the implementation of the command passive interface on the router Daule. This command lets or enables the send of the route's updates through the loopbacks. Here we can see the implementation of timers on the 3 routers, Guayaquil, Daule, and San Borondón. And finally, in this slide, we can see the result of the command show IP route in order to see the route or the default route. In summary, as we said before, RIP works fine on the small network applications or configurations like 5 to 10 routers, for example, or it's suitable for host applications. One of the advantages is the fact that if you don't want to set every route by hand or one by one, you only apply RIP to the default router or any other router of the local network to send the host the information, the updated routing list every X time, a previously defined time. Thus, this is not suitable for mesh networks. Thanks for watching.